Okay, welcome to our last set of videos on electricity, and this is going to be a pretty, if I get it right, it's going to be a pretty demonstration-heavy set of videos today. And we're talking about magnetism. And really, you can't just write about magnetism, you have to see it in action, because while there's not a lot that can be asked about magnetism, at least on the Regents level, the stuff that you need to know is much better visualized than anything else. So, let's get started. We used to think magnetism and electricity were separate phenomena, but they actually have the same root. Back in the 1800s, we discovered that electricity and magnetism actually arose from the same basic phenomenon. It's like looking at two different sides of the same coin, like a heads and a tails. Not that they're opposites or anything, but that it's just two aspects of the same thing. Magnetism, like electricity, happens because of the effects of electric charges. Okay, it's all based on electric charges. Specifically, magnetic effects occur when you take electric charges and you make them move. So whenever charges move, that doesn't need to be pluralized, that is what causes magnetic effects. So let's say we have a positive charge right here, okay? And we know the electric field for that positive charge would look something like this. Okay, it goes straight out away from charge, and this particular charge is not moving. I'm telling you right now, like I'm just saying, if this charge wasn't moving, if it was stationary, a stationary charge creates only an electric field. So if you have a charge that is not moving, it only creates an electric field. On the other hand, look at my great art skills here. Now we have a charge that's moving. A moving charge, a moving electric charge, creates both. Moving charge creates both an electric field and a magnetic field. Why is that? That's just the way it is. Moving charges create magnetic fields. Okay? So you might ask, if you have a permanent magnet, maybe one like this, the north and a south pole, if you have a permanent magnet, are there moving charges in that? Like, what's going on? A permanent magnet is created because the atoms inside of that permanent magnet are all lined up in a certain direction. Okay, and it's much more complicated than this, but essentially they're all aligned in a certain direction. The atoms themselves are like tiny little magnets that when you add them all together, it creates a much larger magnet. So if you really want to know about this, we get into talking about the electron orbits and the spin of certain particles, which is not spin like you guys are thinking of, but that's essentially what you have to get into to really understand this. For your guys' sake, all you really need to know is that for something that is unmagnetized, you have these electrons or these atoms, and they're all they're not lined up at all. Okay, some metals, not all metals, but some metals such as iron, you can magnetize, and a magnet is just an object that retains that alignment over a long period of time. The alignment can weaken, as I'll show you with some of these magnets, but it's something that it holds its magnetic properties over a long period of time. And again, just in case you're curious, when I say alignment, the atoms are all aligned, I don't mean like they're in little rows or anything. It's not about the structure. It's about, well, it has to do with, among other things, the direction that electrons orbit inside atoms. Okay? Now, some things you probably knew from elementary school or middle school. Each magnet has a north and a south pole. Again, we'll get to a lot of demonstrations in a little bit. I'm just trying to get all the note part out of the way. as you can see on this one, where it has very clearly defined N and S for north and south. And they have the same attraction repulsion properties as electric charges. Like poles will repel each other, and opposite poles attract. So, we take these two magnets. We see the south end of this one, the north end of this one. Nope. There we go. They stick together. If I take south and south, nothing. South and north, they stick together. By the way, and you guys will see exactly what I mean by this in a second, these are pretty cheap magnets. They're not really great at holding their magnetic properties, but again, I'll show you that in just a second. So how do we read, how do we use this? What's one way to utilize these properties? Well, first of all, we have things called compasses, right? A compass is used to tell the direction of a magnetic field. Remember, an electric field is the change in the space around an electric charge. A magnetic field is very, very similar. Magnetic field is the change in the space around a magnet. So, here is a little compass, okay? My compass is off-center because I have a bunch of magnets on my table right now, but it points, as you guys know, in the direction that's more or less north. I think north's actually that way as I'm doing this, but I do have some very strong magnets right over here and some magnets off the screen a little bit that you guys can't see, so that's why it looks like this. But anyways, a compass will point in the direction towards north. Set the compass down for a second. So typically it has two ends. One's colored red or white and the other is black. This one, you don't have that. You just have a little arrow that points north, meaning the other direction must be south. The red or white end, if you have a colored compass, the red or white end always points towards Earth's magnetic pole. Oh, excuse me, magnetic north pole. It's kind of important to say north. Okay? So the end, in this case, with the arrow, points towards Earth's magnetic pole, which is not the same thing as the geographic North Pole, but it is very, it is in that general area. You might have heard things about the poles flipping. That happens over very, very long time periods, that's true. But essentially what we're talking about here is something that is more or less to our north. Okay, pretty, fairly close in the grand scheme of things to the north, to the geographic North Pole. So, if you think about it, if this arrow, because a compass has to be magnetic in order to respond to magnets. If the arrow is pointing towards the North Pole, that means the arrow part is attracted to it, which means the arrow is actually the South Pole of the compass, if you think about it. So the South Pole of the compass points towards Earth's North Pole, magnetic North Pole. So if you have something like this, here's my little sketch of a compass. Okay, I'm going to color this end in red. And let's just pretend that this was, I know it's white, but let's just pretend that's like the black part of the compass. So, I have north, west, south, east. And this, even though it points north, just know that it is the South Pole of the compass, which is a magnet, of course. Compasses have to be magnetic, otherwise they wouldn't work. Okay. Now, to talk about the magnetic field, we draw what are called magnetic field lines. Just like electric field lines, what they do is they show the strength and direction of magnetic fields. If the field lines are closer together, that means that the field is very, very strong. And yeah, I'll draw the picture for you right now. Actually, no, let's hold off on the picture a little bit. We can always come back to that. Let's do some demonstrations. Let's talk first about that north and south, the attraction and repulsion. So you guys got this already. You guys know that south and north attract each other. One little cool thing that I like to do is to take a magnet. All right, you're coming with me. Take a magnet and it only works if you get it in the right spot on the table. Let's hope this is the right one. Ah, there we go. Okay, so you can see that I have the north pole of the magnet, and I'm attracting, caught me. I'm attracting the south pole. No, it has to be on exactly the right spot. There we go. This table's a little rough for it. There we go. Come on. But anyways, you see that the effects that we can have with south and north attracting each other. It works the same way as well. If I flip it around and have the south pole here, I can repel them. Come on. There you go. There we go. Kind of neat. But there is actually a problem with these magnets as is. I'm going to set down this pair and I'm going to go back. And the reason we know that there's a problem with this is because of how the compass reacts to these magnets. So the compass, we know, should be pointing north. That's the south pole of the compass. So you'd expect the south pole of the compass to be attracted to the north pole of the magnet. If I bring the magnet over here, you see that that's not the case. You see that the north pole of the compass is actually attracted to the, can you see that that's north? Yes, you can see that the north pole of the compass is attracted to the north end of this magnet. You can actually demagnetize magnets. It is possible. And these magnets have lost their magnetization over a period of time. So what we have to do is we have to remagnetize them. Okay, and you know what? I think I'll show you the remagnetization in a little bit, maybe in the next video. But just keep it in mind that you can have magnets lose their magnetization. Let's see, what do I want to show you right now, though? I think I can show you some magnetic field lines. Just moving some magnets out of the way. So here's what I'm going to do. I'm going to put this bar magnet north, south. I'm going to put it under this piece of paper. Okay, so it's under the piece of paper. And what I'm also going to do is I'm going to take this jar of iron filings. I'm going to sprinkle them around the bar magnet. So give me a second while I get this open. Okay. All right. So now, these are just very simple iron filings. Maybe not iron, I don't know what they are. Magnetic chips. Let's see, does it say? No, just magnetic chips. And what I'm going to do is very gently. All right, this isn't working the way I wanted it to. You see how the chips are kind of aligning in a certain direction? That's what I want. About a few more. Okay. So this is a way you can actually tell the shape of the magnetic field. When you drop these iron chips onto the magnet itself, what you start to get is the pattern, because the magnetic chips, they're magnetic themselves, they align themselves with the direction of the magnetic field. So you can see that for a bar magnet, you can kind of see the outline of the bar magnet right here. For the bar magnet, what you get is these kind of looping patterns like this. Okay? Now, if this was an ideal bar magnet, you would have all of the lines coming directly from here and here. Like I said, these magnets are kind of cheap. But it still gives you a general sense of the pattern. They start at one pole and then kind of curve or arc down into the other. Fun to play with. Okay, so let's go back and let's actually draw this out. Okay, so for a bar magnet, the shape that you will draw will look like this. bar magnet magnetic field lines start at the north and they curve all the way around. And the arrow, because of course we need an arrow, points towards the south. Kind of look like it's had big ears. Now, if you were to put a magnet in or a compass in this, which way would the compass point? Well, we know that the compass, the south pole of the compass will point towards the north pole of the magnet. So if I'm drawing my little compass here, I've got it looking like this. The south pole, the colored end, the red or black or white or whatever. I think it's either red or white usually. The south pole of the compass will point towards the north pole of the magnet and vice versa. North pole of the compass points towards the south pole. This right here is the last thing I'll show you right now, and this is called a horseshoe magnet. A horseshoe magnet, if this is north and this is south, again, magnetic field lines always point from north to south. Just like electric field lines always point from positive to negative, magnetic field lines always point from north to south. So it just looks like this. And if you were to put a compass near this, you would see that the south pole of the compass points towards the north pole of the magnet. I can show you a horseshoe magnet really quick. There we go. And of course it's attracting everything on the table because it's extremely powerful. So remember, the south pole of the compass points towards the north pole of the magnet. Here's my compass. You can see the arrow right there. Arrow's pointing towards this guy, pointing away from this. So that means south pole of the compass, north pole of the magnet, south pole of the magnet. Cool. When you guys come back, I will show you how to remagnetize things along with a couple other neat little demonstrations.